about some high-dimensional contact topology, which is a nice continuation from the first talk by Roger. Everything I'll say today is joint work with Jonathan Bowden, who's in Australia, and with Fabio Gironella, who's sitting right there, so you can also bombard him with your questions. So the paper is already up in the archive. You can find it here. We put it up, I think, last week. It's a long paper, but I hope more or less readable. Anyways, so in order to first set up some notation, let me just remind you of what it is, an open book decomposition. Thank you, Roger, by the way, for mentioning open book decompositions in the last talk. So my notation will be an open book for me. I'll write OBD sigma phi. M is just going to be some sort of a geometric decomposition of a manifold M into two pieces. So here, sigma omega is a Liouville domain. And I look at B, which is the boundary, and I'm going to have some co-neighborhood of the boundary of the page sigma, and I'm going to have some mapping torus piece. Where phi here is the monodromy of the open book. And here sigma is the page. Okay, so this is the notation that I will use. So the story basically starts with the following theorem by Bourgeois in 2002, which basically, it's a construction, right? So you start with some contact manifolds, MC. Sorry? Any dimension, right? So here, sigma is 2n dimension, so this guy is 2n plus 1 dimensional. Well, let's say, yeah. So I start with some 2n plus 1 dimensional contact manifolds, and I take some supporting open book decomposition. Where supporting here is in the sense of Giroux, so there's a Giroux form which gives us a contact structure, and it's adapted to the geometry of the situation in some specific sense. So with this data, you get an associated contact manifold in the product of M with the two torus. And I'll denote this by Bourgeois of sigma phi. So basically, what's really being used here is the existence of supporting open book decompositions by Giroux. This is just, you write down a contact form, you check the contact condition, done. Right? The motivation behind this at the time was basically to construct examples of high-dimensional contact manifolds. In particular, if you start with a T3, with the standard contact structure, this gives every odd-dimensional torus is contact, which 2002 was still unknown since works of Lutz in the 70s. So it was an interesting construction at the time. In terms of constructing examples of high dimensions, now we know a very powerful theorem, which was proven in 2015 by Borman, Eliashim, and Murphy. So basically, you can say that in any dimension, contact structures exist whenever the obvious topological obstructions vanish. But the contact structures that you obtain are flexible, right? They satisfy H principles in the sense of Gromov. So in some sense, they're not really geometrical. They're more topological in nature. So the first result that I want to state today, in some sense, says that this construction runs in the orthogonal direction. So they're very much not the over-twisted contact structures constructed, given by BEM. So this is the first result, tightness. And let me mention, before I state the theorem, some work done by other people. So there's a result by Lisi, Marinkovic, and Klaus Niederkruger. So this is LMN. So they basically give examples of some Bourgeois contact manifold, which is, or let's say, there are examples of Bourgeois constructions which can be tight, even though the original starting manifold was over-twisted. So in some sense, the over-twisted property is not something that stabilizes under this construction. Another result in this direction, in dimension 3 by Fabio, which basically says if the first Betti number of your 3 manifold is non-zero, then there exists some open book such that the associated Bourgeois is actually hypertight. Which implies tight by work of Hofer and Albers in higher dimensions. So these are instances of, yes? Hypertight means that there exists some contact form which admits no contractible Rabe orbits, which implies tight by work of Albers and Hofer. So in other words, if you have something over-twisted, then you run the holomorphic curve machinery and you find some contractible Rabe orbit. So this implies tight. So the first theorem, theorem 1, which is Bowden, Gironella, and myself, says that at least in dimension 5, these are particular cases of some more general phenomena. So in dimension 5, the Bourgeois contact manifold is always tight. Namely, independent on the starting contact manifold and the open book. And in that sense, let me mention that the Bourgeois construction depends not only on the original contact structure, but also on the starting open books. You can have 2 supporting open books for the same contact structure such that when you do this construction, the results are non-contactomorphic. So this is independent of whatever original data you started with, at least in dimension 5, say. Sorry? Yeah, so this is surface. So yeah, thank you. Okay, good. So in other words, we already have many examples in the literature of flexibilizing a contact or a symplectic manifold, right? Say in dimension 3, you can always take Lutz twits. So whatever you started with becomes over-twisted. Say if you start with any Weinstein manifold, you can flexibilize it to get a flexible Weinstein manifold. In some sense, what this says is that this operation is tightifying, so it's orthogonal in some sense. So you start with anything, you make it more rigid. The price that you pay is that you're changing dimensions. Right? And let me also say that this result is also sharp with respect to taking branch covers. So there are already examples of double branch covers such that what you get is actually over-twisted. And those actually were the first examples of over-twisted, of PS over-twisted contact manifolds on closed manifolds. Sorry? It's a branched cover along, so you yeah, okay, good. So any questions in the first result? Okay. Good. So the second part of the story has to do with symplectic fillability. Once you're given a contact structure, the first thing that you want to understand is what's its nature, whether it's tight or is it over-twisted or rigid, or is it a flexible object. The second thing that you want to understand is, does it actually admit symplectic fillings, and if so, how many? Because, we know by work of Ramos and Eliashevich that whenever you have something which is fillable, then it's tight. Right? That's sort of the motivation, say. In that direction, let me mention the following results. We have Masur, Niederkruger, and Wendell. Which already tells us that if you start with some contact structure which is weakly fillable, then the associated bourgeois is also weakly fillable. Independent on the open book. So weak fillability is some property that stabilizes. Another result by Lisi, Marinkovic, and Wendell, and Niederkruger, says that if you start with some subcritically Stein-fillable contact structure, then the associated bourgeois is Stein-fillable with respect to the open book given by Seeleybeck. This is by a result of Seeleybeck, equivalent to admitting an open book with trivial monodromy. Then, if you start with such a contact manifold, then the bourgeois is actually Stein-fillable. So, I mean, Stein-fillability is not really some property that stabilizes under some pretty strong restrictions on the original contact manifold. So what we want to consider for this talk and in the paper is, well, a slightly restricted case, namely the case where you start with a three-manifold which is planar, so it admits an open book with G0 pages. So the planar case is my manifold is three-dimensional, and the genus of the page is 0. So in this case, already in dimension 3, there's the following theorem by Chris Wendell, which says the following. So if you start with some symplectic, a strong symplectic filling of a planar contact 3 manifold, then the symplectic manifold admits a very special structure. It admits the structure of a Lefter fibration. Which induces the original open book when you take the boundary. So inducing the original open book at the boundary. Okay, so the machinery for this is, of course, a holomorphic curve. So whenever Roger sees a Legendrian, I see a holomorphic curve. And the planar assumption has to do with analysis. So the fractal theory is well behaved for G0 curves. So they have the right index and so on and so forth. They come in nice moduli spaces. OK, so corollary of this are twofold. So the first is, well, let's say minimal fillings of a planar contact 3 manifold are actually in 1-1 correspondence with decompositions of your monodromy into products of positive Dane twists. So in some sense, you go from studying fillings of a planar contact 3 manifold reduces to some problem in geometric group theory, namely the mapping class group of a genus 0 surface. And actually, strong fillings in some sense exist in abundance in this case. The second corollary is if you start with a planar contact 3 manifold, then Stein fillability is equivalent to strong fillability. Right? Because Lefschetz probations are in some sense naturally, well, by a result of Eliashberg, they admit Stein structures. Okay, so the question that we want to ask is how much of this picture actually stabilizes under the Bourgeois construction in dimension 5? And the answer to that is a bit surprising, at least for me, even more than this result, which is already a bit curious. So the theorem is the following. So theorem 2, by the same people. So it says the following. So if you start with some planar contact 3 manifold, and so here phi is the monodromy, then the associated Bourgeois is going to admit strong fillings only in the most trivial case. So it admits strong fillings if and only if phi is trivial. So in other words, this picture here, which tells you that in the 3-dimensional case you have a lot of, you can sort of quantify how many fillings you have. When you stabilize, all of that is killed. Not only over-twistedness is killed, in some sense, fillings are killed. Okay. Any questions? Okay. So corollaries of this are the following. So here we assume the planar case. So if you start with some product of positive Dane twists, which is non-trivial, then the associated Bourgeois construction is actually is weakly but non-strongly fillable. So it's a weakly but not strongly fillable contact 5 manifold. Right? It's weakly fillable because the original one is Stein fillable and particularly weakly fillable, and that's a property that stabilizes. It's not strongly fillable because of theorem 2. The remark here is that the first example of such manifolds were constructed by Meusseau, Kruger, and Wendel, also in dimension 5, and they also look like, smoothly, they look like a 3-manifold times T2. But those kinds of structures are actually associated to what's called a Liouville pair on M, which implies in particular that the 3-manifold is co-fillable. So it's one contact boundary component of a symplectic manifold with disconnected boundary. And those, unfortunately, we don't have so many examples in general. In dimension 3, there are a bunch. In higher dimensions, we also have examples by Meusseau, Kruger, and Wendel, but I mean, they do not abound. The good thing, the advantage of this result is that it gives already a new class, precisely because in this case, M is actually never co-fillable by a result of Ednayer. So this means that this actually are not the same as the original ones constructed by these people. So they, in some sense, they complement them, and they're actually more abundant. Right? You take any non-trivial product like this, and you get an associated such contact phi manifold. Okay. And the second corollary is that it's, again, a sort of a stabilization of the corollary over there, that Stein fillability is equivalent to strong fillability. Of the associated bourgeois. Right? Because in the trivial case where the monodromy is trivial, you can actually write down a very explicit product, Stein filling. Yeah.
You have a three-dimensional Giroux domain times a large neighborhood. Does that obstruct strong fillability?
If you have a three-dimensional Giroux domain and a huge neighborhood disk. I mean, in some sense, this is saying that you won't have that, right? I mean, maybe we can discuss later. I mean, I don't know off the top of my head. Okay, and so we discussed tightness, we discussed fillability, and now I want to discuss some application which somehow popped out of this whole story, out of the technique developed to prove these theorems. So the application is the following, and it starts with the following observation. So the observation is if you take the unit cotangent bundle of Tn with its standard Stein-fillable contact structure, then this is a Bourgeois manifold. So this is Bourgeois of the page is d star t n minus 1, and the monodromy is trivial. So in this case, well, we know on the one hand that, of course, they're Stein-fillable, and also on the other hand, too. But the theorem, the result, is that such Stein-filling, the standard one, is a unique such, well, strongly spherical filling up to diffeomorphism. So this contact structure here admits a unique, let's say, symplectically spherical filling up to diffeomorphism. And this is already a generalization, let's say a high-dimensional version of a result by Chris. So in dimension 3, Chris showed that T3 with a standard contact structure admits a unique filling up to symplectomorphism. So you actually remember the symplectic structure. This is a bit weaker, but it's in any dimension. So this is a smooth version of that. And let me also, okay, yes. So any questions? This is a stop to breathe before I go into the actual construction and try to, if I have time, sketch some proof. Okay. Good. So let me just be a bit more explicit about what the Bourgeois construction is. So we start with our Livre domain, which is a page. We start with our monodromy. Which has to be, I mean, it has to preserve it has to be an exact symplectomorphism. And here I'm going to the node B, the boundary of the page, which is a binding. Right, so we've got the open book decomposition. Sigma phi with the Giroux form, which we'll write down usually as like this. So I'm going to call this alpha b plus r squared d theta union the mapping torus piece. So theta here is sort of the S1 parameter, and r here is a radial coordinate. And this is glued along the binding times S1. Right? So this is the geometric picture for M, and then we do the Bourgeois. Right? So we also have a similar decomposition, which is take the product with T2 of each piece. Let me just write it on the other board. So the Bourgeois now is take the product with T2 of this whole thing. Right? So I've got this first piece, but the point is that I want to see this guy as the unit disk cotangent bundle of T2, which is trivial. And the contact form basically looks like this. So you take alpha b plus, and you take the standard Liouville form on d star T2. This is the first piece. And then I have a second piece, which looks like this. So I've got the mapping torus piece times T2. And then the contact form, well, it looks something like this. Lambda plus d theta plus some terms here, cosine theta dx minus sine theta dy. I mean, whatever, it's some formula here. Here, x and y are coordinates in T2. And I want to call this whole chunk, I want to call this alpha T3. So the point that I want to make here is that I want to think of this as two pieces glued together. I want to think of this piece as fibering over Liouville domain. So the unit disk cotangent bundle of T2 with its standard Liouville form. And I want to think of this piece as fibering over S1 times T2 with this contact form here. So the first piece is a fibration. It's a contact fibration over a Liouville domain. Contact fibers it's just the binding. And the other piece is a Liouville fibration over a contact manifold. So in some sense, the roles of fibers and base are reversed. So this is what I want to call a supporting spinal open book decomposition. Or SOBD. These spinal open book decompositions were introduced in work of Sam Lacey, Chris, and Jeremy Van Horn-Mars in dimension 3. And there's also a notion in higher dimensions, which is basically something like that. So two fibrations glued together compatibly. And those structures, mimicking Giroux's correspondence in some sense, support contact structures. And this is one such instance. So even though, when you do the Bourgeois, it may have some supporting open book decomposition by general work of Giroux, I think the most natural the most natural way of thinking about this is you start with an open book, you stabilize, you naturally see a spinal open book supporting the contact structure. Okay? And I want to use that underlying decomposition in order to prove the theorems. So here's where I'll start the sketch of theorem 2. Right, so this is the fillability results. Remember, I want to prove that in the planar case, fillings are only existent in the trivial monodromic case. Right, so how does such a thing start? So we're going to use some holomorphic curve machinery, right? In some sense, that's what we should, because the results already somehow say that this is a very rigid construction. There's no wobbly stuff. There's no H principle happening. So they're amenable in principle to holomorphic curve techniques. So we start with some strong filling of my Bourgeois manifolds, where this is planar. And now I'm going to try to mimic the proof in dimension 3 and see what happens, basically. So we start with the, so I'm going to draw a picture. So here's. So here's my contact manifold. And here's the symplectization. Let's say this is, so here's my filling. So this is the completion, right? And here's my decomposition. So I want to call this piece here, this is MS, which is the spine. And this is MP, which is the paper. And the pages are the original pages of the original open book, sigma. And the point here, the important point is that the monodromy of this vibration here, it's the original monodromy of the starting open book phi and the identity on the second factor. So this is an important point here. So I start with my geometric decomposition of the manifold, so spine and paper, and then I want to do the holomorphic spinal open book construction, which we already somehow know from the literature from the open book situations. So I want to construct, I want to take some data of holomorphic, of an almost complex structure, and I want to construct a foliation of the cylindrical end. And somehow it starts by looking like this. So I've got my page here, which starts being constant in the r direction, and then it picks up a cylindrical end, and it becomes asymptotic at infinity to the binding times due to the stabilized binding, which is a bunch of ray orbits, right? So here, the topological type of this holomorphic curve is the Leuva completion of sigma. So it's a genus 0 holomorphic curve, which is asymptotically cylindrical. And I have a foliation, something that looks like this. So you need to have some imagination here, of course. And now the point is that this foliation is finite energy, so everything is regular, so the moduli space of such curves is very nice. So they will start to come inside the filling and do some stuff. So they will come in, and they will start behaving in some way, and who knows what they do. And now, the main difference between this 6-dimensional situation and the 4-dimensional situation is that, in principle, I've lost positivity of intersections. Right? Positivity of intersections is crucial in dimension 4 to obtain all sorts of results. It's like the magic of low dimensions. Dimension 6 or higher, I have no such thing. So in principle, the holomorphic curves might start self-intersecting or intersecting each other. I mean, whatever. I have no idea what happens in the interior. Right? But one of the crucial observations is that I do have control over what happens over here. And I will state that as a theorem now. But so from this picture, we'll obtain some moduli space. Moduli space M of punctured holomorphic spheres in the completion of W. So this is my W hat guy. Okay. So for the purposes of this talk, I will simplify my life, and I will assume the following. I will assume that W is symplectically spherical. In other words, I mean, there are no bubbles in the moduli space M. This is a severely simplifying assumption. At least, I mean, we actually proved everything originally in the symplectically spherical case, and then suffered a long time with bubbles, which can be multiply covered and blah, 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 blah. Right? So the theorem is actually proved in the general case, but in this case, the actual results that you get are actually stronger. And let me also mention that in the application, right, we also, in some sense, classified symplectically spherical things. What's behind everything is that, as opposed as in the four-dimensional situation, in which you can blow down exceptional holomorphic spheres, in higher dimensions, I mean, at least I don't know of a coherent way of blowing down bubbles which might come in two-dimensional families or higher dimensional things. I mean, maybe it's some technicality. I have no idea. But this simplifies life a lot. So the theorem that I want to state is, it has to do with the moduli space itself. So now, basically, the whole proof relies on understanding the structure of this moduli space. So the first claim has to do with the compactness. So the point here is that the moduli space will be Gromov compact, which is the absolute key point of the proof. In other words, there are no bubble degenerations, well, because of my asphericity assumption. There are no multiple level holomorphic building degenerations. There are no degenerations having to do with the non-contractible vanishing cycles on the page, which is precisely what's different from the four-dimensional situation. In the four-dimensional situation, vanishing cycles are precisely what gives you non-trivial monogermy. The claim in here is that such a thing is ruled out in this particular situation. So this is, maybe if you've seen this stuff, this is pretty much hard to believe, but I'll try to convince you by the end of the talk, if I have time, that such a thing is actually true. The second property is the asymptotic foliation property. So this property says that basically if I look sufficiently far away to the horizon, I look really close to infinity, I see a foliation. So for every p in some neighborhood of infinity, so here A0 is huge. There exists a unique element in the moduli space such that it goes through this point. If there are bubbles, such a statement is actually non-true. But in this case, we see it's sort of this asymptotic foliation property. The point is that now the moduli space has a natural boundary which can be identified with the original Bourgeois manifold. And the third point is the homeomorphism type of M. Actually, you can identify M, at least topologically, with D star T2. Right? So what's happening here, in some sense, is the most natural thing that could happen. So you do, in dimension 4, you do this moduli space stuff. What you see is a Lefschetz fibration where the base is a D2. What's happening here is that where you see, in some sense, it's some Lefschetz fibration type thing, whatever that means, such that on the base you have a stabilized D2, and this is what this is saying. So there's a picture here. So let's assume the theorem. Let me finish the proof. I mean, this is the whole workhorse result. Right? This is where all the hard stuff is hidden. So assume the theorem, and so we've got the following picture, right? We have the marked moduli space. We have a forgetful map, which forgets the marked point. It's called pi. So here's a four-dimensional moduli. Here's a sort of a six-dimensional object, and we have an evaluation map to the completion of W. And now that property, or rather the asymptotic foliation property, tells us that the boundary of this marked moduli space is identified with the Bourgeois manifolds. And this, as we observed before, so this is the boundary of W, already comes with some sort of underlying structure. It has the spinal Bambouk decomposition, which induces such a structure on the boundary of the moduli space by the evaluation map. So in other words, the marked moduli space has a horizontal boundary, it has a vertical boundary. And here, this is basically corresponds to, under the evaluation map, it corresponds to the spine. And under the evaluation map, this corresponds to the paper. And this, in particular, it fibers over S1 times T2 with this monodramy. It's some sort of stabilized version of Wendel's result. So now I've done all the symplectic geometry that I could. I constructed my moduli space. I got some really sort of vibration happening. I throw away the filling, and now I do smooth topology with the moduli space. So remember that we want to show that the monodramy is trivial, and dimension 2 being smoothly trivial is the same thing as being symplectically trivial. So I can do smooth topology on the moduli space and still prove some result having to do with some symplectic information. So the picture is something like this. I've got my sort of marked moduli. So this is M star. And here's my fiver, which is a copy of sigma, fivering over a point here, which is the unmarked moduli, which is a copy of D star T2. Right? I mean, the way you identify the moduli space with D star T2 is this is foliation here. So I take a base of the spine, which is a copy of D star T2. And the claim is that every curve intersects that D star T2 precisely once. So this gives an identification of M with this guy here. And here we've got the vertical boundary, which is the paper piece, fivering over the boundary, which is a T3. And here we've got the upper lid, which is precisely the other piece, the spine. Right? Right, so now, well, compactness says that there are no degenerations, so the fibers are all the same. So this is a vibration. So here we've got a vibration. And here we see the monodramy, phi times identity. But now this phi bounds a disk in the base, which is a cotangent fiber. So if you have a vibration, and if you have a circle which bounds a disk on which you see the original monodramy, then the monodramy better be trivial. Okay, so compactness is the key here. And how much time do I have? Okay. So let me try to convince you how you actually prove the key point. Yes. Yes. Well, the evaluation map is giving you the diffeomorphism in the boundary. And sometimes, I mean, you've taken your filling, which is, I mean, you've foliated somehow. I mean, it's not really a foliation, it's some homological foliation, whatever that means. Like for every point, there's a curve that goes through it. In the interior, you might have more than one curve going through a given point. But at infinity, you don't. So in some sense, you take your filling and you make it nicer. Because now you look at the domains of the curves. Now you separate the domains, but you still remember the boundary. And now you have a nice vibration structure. That's what's happening. Any other questions? So, okay. So key point, right? Which is compactness of some moduli space. So what we actually want to rule out are configurations like this. So you have your page, and then in principle, it might degenerate to something which might look like this, for example. You have some node here, and then it glues to the topological type of your page. And this would correspond to some non-contractible vanishing cycle. Contractible vanishing cycles correspond to bubbles, and I'm assuming that problem away. In the general case, I do have to deal with that problem. It's a nightmare. And yeah, so that's what makes everything very technical. So we want to roll this stuff out. So this is a claim. This stuff cannot happen. So how do we do that? Well, this is a very involved, long story. So the proof actually involves using 2 extra moduli spaces, as follows. So first, there's a notion of a surgery, just spine removal surgery. So what is this? Which sounds very surgical and scary. So the name was actually introduced by Chris and Lissy and Jeremy. So I guess these guys are very creative. And this is already a generalization of a construction by Yasha, this capping construction, which you start with an open book and you cup the pages, and then you get some sort of symplectic fibration over S1. So this is a version of that. So smoothly, what's happening is I take my Bourgeois manifolds, you remove the spine, and then you glue in some sort of handle. So you glue in as many copies as boundary components of your page along the boundary of your page times T2 times S1. So you glue in a handle which looks like D star T2 times D2. Right. Some sort of stabilization of Yasha's construction. And now the point is that you obtain a new manifold which is not precisely a contact boundary, but it's a stable Hamiltonian boundary. And in particular, it's full of holomorphic spheres. So the picture is something like this. You have your filling, W. Here's your Bourgeois guy. And then you're going to attach a bunch of handles, as many as boundary components of your page. So here's your page sigma, and I'm going to push it to the filling. Let's say we have a cylinder, just for the purposes of the picture. And now what you basically do is you cap those pages with the cores of the handles. So you see a sphere, and it intersects the co-core precisely once. And the co-core is a copy of D star T2. And we have as many as boundary components of the page. So this is a transverse intersection, and both of them can be made holomorphic. So now you complete this whole thing. So now you've got, this is what we call W cap. So this is a capped cobordism, and then we complete the cap cobordism, we get a completed guy. Right? And now the point here is that this guy is ridiculously full of holomorphic curves that probe the topology of the original filling. So on the one hand, the resulting boundary is now a copy of so this is W cap. The boundary of this thing is a copy of S2 times T3 with some stable Hamiltonian structure, H. But this stable Hamiltonian structure is in such a way that this S2s here become holomorphic. So this gives us a moduli space MS of spheres. The first factor gives a moduli space of holomorphic spheres. The kernel of the stable Hamiltonian structure looks some sort of like confoliation. So it looks like T star S2 plus the standard contact structure on T3. So it's an integral piece plus some contact piece. And now when you complete this, you see spheres, but you also see a cylindrical end over T3. And you can also use that to get another moduli space of holomorphic cylinders, which was originally used by Chris in the 3-dimensional, 4-dimensional situation. So this is the first factor, but now we also observe some completion of, so we have, the cylindrical length looks like some end times S2 times T3. This gives us the spheres, but this other sort of piece gives us a moduli space of a Wendell family of cylinders. Which is, in some sense, S2 parametrized. Right? So this gives us a lot of ways of probing the original manifold. Okay, so now with this moduli space, if you look at this picture here, which is when you complete this D star T2, this holomorphic cocore becomes a T star T2, T star T2, which is a holomorphic hypersurface with cylindrical length. And in this situation, actually, one can use some souped-up higher dimensional version of C-Frank intersection theory to obtain the claim that somehow these holomorphic cylinders, which you see here, actually come in hypersurfaces. So there's a foliation by hypersurfaces. Inside each leaf of that foliation, I see another foliation of cylinders. And for that, you need to intersect with the hypersurface and use this machinery in order to obtain that claim. So this is a very, very nice sort of foliated situation in the end. In the interior, there might be some crap happening, but on the nose, you already have some very good control up here. So in other words, let me just state it like this. So MW comes in hypersurfaces. Hypersurfaces. Each leaf of this foliation up there is a copy of either a T star T2, if you complete one of the cocores and one of its translates, or a symplectization of T3, if you're away from the handle. Okay, so what's the step one in order to get the key result? Step one is, well, using the moduli space of spheres, we conclude that the following inclusion, point times T2 times point, where point here is any point in S2, and this is any point in S1. So when you include this inside the boundary of the capped guy, and you include the boundary of the capped guy inside the capped guy, so this whole composition is injective in homology. In other words, I mean, this guy remembers the T2 factor, at least homologically. It really wants to pop out some product factor of T2. And so that this is some sort of homology statement of that. So this is the first step. The second step is, so from step one, you conclude that the Wendell moduli space, the Wendell family, is compact in the symplectically spherical case. So in other words, there are no degenerations of the cylinder to a bunch of things. So again, we get some sort of vibration. And once you conclude this, so again, this is the spherical case. The last step, step 3, is, well, from step 2, well, you conclude that if a spherical class in H2 of the capped cobordism intersects one cocore, then it actually has to intersect all of them. It intersects all of them. So this is some sort of statement about the intersection theory of the capped cobordism. So now, assuming this whole, 3 steps, what happens if you actually have such a configuration? Now, this happens in the original uncapped manifold, where these guys correspond to the binding. So now, topologically, smoothly, you just add infinity, and then you cap. So you add the cap in cobordism, and now you cap with the cores of the handles. So what you see here are two spheres. And in particular, if you have such a generation, there exists one sphere which intersects one of the co-cores, but not all of them. And that's the end of the proof. And I'm done. Yeah.